Hello friends, the topic for today is floating point numbers IEEE standard formats. The fixed point number representation has a fixed position for radix point and a fixed number of digits to be to the left and to the right of the radix point. So very large numbers cannot be represented, nor we can represent very small fractions. A floating point representation allows a large number of expressible numbers to be represented in a small number of digits by separating the digits used in the precision form, the digits for the range. The floating point number can be characterized by a triple of numbers, sign, exponent and significand, and it has a floating point binary point. That's why they are called as the floating point numbers. In today's video, we'll discuss the floating point numbers IEEE standard formats. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to our channel, kindly subscribe and press the bell icon so that you get notifications for future videos. Let us start the topic floating point numbers IEEE standard formats. We'll start with the introduction. The fixed point numbers representation has a fixed position for radix point. So the radix point is fixed and we have digits to the left and right of the radix point. So this representation will need many digits in order to represent a practical range of numbers. In scientific calculations, we have a great range of numbers such as say the constants, scientific constants, Avogadro's number, that is 10 raised to 23. So this is a practical range of numbers is very large. That's why they cannot be represented with the fixed point numbers. With fixed point notation, say for example 2's complement, it is possible to represent a range of positive and negative numbers centered on 0. Then by assuming fixed point or radix point, here this format allows the representation numbers with fractional component as well. But there are limitations. Very large numbers cannot be represented, and similarly very small fractions they cannot be represented. And again, the fractional part of quotient in the division of two large numbers, it could be lost. So with these limitations we cannot use the fixed point notation. We have to go for the floating point numbers. So for convenience, we would like to have a binary number representation that can easily accumulate both very large integers and very small fractions. So to do this, computer must be able to represent numbers and operate on them in such a way that position of the binary point is variable and it is automatically adjusted as computation proceeds. So in this case, binary point is said to float and the numbers are called as floating point numbers. So we are able to change the position of the binary point. So that process is called as normalization. So after normalization, we can represent a large number and a small fraction with the help of the floating point numbers. Now since the position of the binary point in a floating point number varies, it must be indicated explicitly in the representation. So this will be done with the when we do the actual normalization. Now here for decimal numbers, we get around this limitation by using scientific notation. We have scientific notation. For example, if you take number 976, then 0 0 0 0 0 0 0 0 0 0 0 0. Now this can be represented with 9.76 into 10 raised to 14. So here we are given a decimal point after 9, and then these are the 7 6 two significant bits we have taken and multiplied with 10 raised to 24 exponent form. Similarly, a very small fraction 0.000976 can be written with 9.76 into 10 raised to minus 14. So here the exponent is negative. So what we have done, actually we have slide the decimal point to a convenient location and use the exponent of 10 to keep the track of the decimal point. So this allows a range of very large and very small numbers to be represented with only few digits. Let us see how we can be applied to the binary numbers. On the same approach, if we take with binary numbers, then we can represent in the form plus minus then m multiplied by b raised to plus minus e. Now this b is nothing but the base. So in case of binary, this will be 2. In case of decimal, it is 10. So we have taken 10 raised to minus 14 and 10 raised to 14. So here we will take 2 raised to plus minus e, that is the exponent. And this part is nothing but the fraction or the mantissa part. So the number can be stored in a binary word with 3 fields. First is the sign, that is it will be a bit 1 or 0. So 1 will represent negative and 0 will represent the positive numbers. Then second part is the significant or mantissa. So it will have some significant bits. So let us see the formats. In that we'll have the significant bits for particular precision. Then next is the exponent, that is e. So this is nothing but the scale factor for the implied base of 2. So that will be always 2 raised to e. So b raised to plus minus e. So 2 raised to plus minus e. That will be the exponent part. Then let us move on to the basic IEEE format or 32-bit representation. So the basic 32-bit format, it is shown in figure. We'll see the figure. The leftmost bit represents the sign bit for the number, and the next 8 bits represent the e, that is the exponent scale factor, and the remaining 23 bits, that is m, they are the fractional part of the significant bits. The full 24-bit string b of the significant bits is called as the mantissa and has a leading 1. So this with the binary point immediately to its right, we will have the mantissa 1 dot m. So this is the binary point. So m is 23 bits and this 1, so that will form the 24 bits. So this will be representing 1 dot. So this is the fraction part of the this. So that's why it is represented b minus 1, b minus 2, b minus 23. And so this, it will have the value 1 plus this all multiplied by 2 raised to minus 1, 2 raised to minus 2, and so on, bits multiplied by this. Then let us see the figure. So you can here, this is the single precision format. So first is the sign bit. So 0 signifies positive and 1 signifies negative numbers. And then we have 8-bit sign exponent. Now this is in the axis minus 127 representation. We'll see the what is axis 127 representation. And then we have the 23-bit mantissa fraction. So that is represented here. So the value which is represented by this is plus minus 1 dot m multiplied by 2 raised to e dash minus 127, because this exponent will be in the minus 127 axis minus 127 format. So we'll have to add 127 to this in order to get the actual exponent. So you can take the example here. Now here we are representing the fraction 0, 0, 1, 0, 1, 0. So 1, now this is not normalized, so we'll have to change the decimal point. So decimal point will be shifted here, and accordingly we'll get the value represented. So if you look at the exponent part, it is 0, 0, 1, 0, 1, 0, 0, 0, 0. So that is nothing but 40 in decimal. So we'll have to take the exponent as e dash minus 127. So that will come out to be 40 minus 127, that is minus 87. So the exponent will be minus 87. So in this way we can represent with the single precision format. Let us see the details of this single precision format. Say by convention, when the binary point is placed to the right of the first significant bit, the number is said to be normalized. So when it is to the right side of the significant bit, so then it will be normalized. And here the scale factor, the base will be always 2 and the leading one of the mantissa. Mantissa is 24 bit. Out of that, this first will be always 1. So they are fixed. So we cannot, they need not appear in the representation. Then instead of actual signed exponent e, the value stored in the exponent field is unsigned integer e dash, that is nothing but e plus 127. So this is called as the access minus 127 format. So e dash is in the range, the e dash is in the range 0 to 255. Now the values for the range 0 and 255, they are called as the special values. We'll see what are the special values, and that's why the actual range for e will be, e dash will be 1 to 254. And so plus and minus, when we want to put it in the positive and negative range, so it will be minus 126 to plus 127. That will be the range. And here the use of access minus 27 representation simplifies the comparison of the relative sizes of the two floating point numbers. Then let us see the single precision further. The 32-bit standard representation is called as a single precision representation because it occupies a single 32-bit word. So the total size of that is 32 bits. That's why it is called as the single precision. So here the scale factor will be 2 raised to minus 126 to 2 raised to plus 127, as the value of this is ranging from minus 126 to 127 plus 127. So this is approximately equal to 10 raised to plus minus 38. So you might have come across this range when you are studied the C language, in that the integer range, particularly double and integer range, that is nothing but this single precision. Then the 24-bit mantissa provides approximately the same precision as the 7-digit decimal value. So here this is the example. We are again repeating the same example. So this 0, 0, 1, 0, 1, 0, 0, 0, so that is nothing but 40. So that represents minus 87 because 40 minus 127 is minus 87. So this is the exponent part. Then 0 here means it is a positive number, and the value represented is 1.001010. So this is the fractional part. It has got two zeros and then 1010 and so on. So in this way we can represent with the single precision format. Then let us see the double precision format. Now, to provide more precision and the range of for floating point numbers, double precision format is specified. Now this is shown in figure. We'll see the figure and see what is the change here. So here you can see this sign bit is as it is. The E dash, that is the exponent part, it is 11 bits access. Now here it is 1023. So in the single precision it was access minus 127. Now here it is minus 1023, because now in that case 2 raised to 8 is 2 raised to 7 is 128, minus 1, that is 127. Now in this case 11 minus 1 is 10, so 2 raised to 10 is 1024, minus 1 is 1023. So the so here we have increased exponent. So 11 bit access minus 123 exponent E dash, it will be in the range 1 to 1046 for the normal values, and we have the special values 0 and 1047. Okay, and so this range will be divided into minus 1022 to plus 1023. So the scaling factor will be 2 raised to minus 1022 to 2 raised to 1023. So that will be approximately 10 raised to plus or minus 308. So this again, this is the double precision value. That is, you might have learned it in the C or C++. Then the last point, the 53-bit mantissa provides a precision equivalent to 16 decimal digits. So single precision was up to 7 decimal digits. Now here it is 16 decimal digits. Let us go to the next part, normalization. So the normalization, say here we have two basic aspects of operating with the floating point numbers. First is, if the number is not normalized, it can be put in normalized form by shifting the binary point and adjusting the exponent. So here we can this is shown in the figure. We'll see the figure later on. So here this is the number 0.0010110 multiplied by 2 raised to 9. Now here we have the some more bits here. They are just, we are assuming that they are there, and now this, the decimal point, it is or the binary point, it is not at the proper place, it is not normalized. So in order to normalize this has to be put here after 1. So 1.0110, so that is how we'll represent this. Now if you want putting it here, that means you are 1, 2 and 3, so 3 places you are shifting. So that's why we have to reduce the exponent by 6, because we are shifting towards right. So since the scale factor is in the form 2i, shifting the mantissa right or left by 1 bit position is compensated by increase or decrease of the exponent by 1. So if you are shifting towards right, you have to decrease the mantis exponent, and if you are shifting towards left, you have to increase the exponent. So here in this case we have shifted to the right side, that's why we have decreased the exponent by 3. Then second point is, say a number that does not fall in the representable range of normal numbers might be generated. So this means that its normalized representation requires an exponent less than minus 126. or greater than plus 127. So in the first case we call it as the underflow because the exponent is less than minus 126. It will lead to the underflows. And if it is greater than 127, we call it as the overflow. So overflow will occur when the exponent is greater than plus 127. Then next is the figure. Now here this number, it is the exponent part is 100010000. If you look at this exponent part, it is nothing but 1 plus 8. This is 128 plus 8. So that is 136. So if you this is 136, that means the exponent is 9. 127 plus 9 is 136. So the exponent part is 2 raised to 9. That's why we have to write here 9 plus 127, that is 136. And this part, now here we have shown 00101. So it is not normalized. That's why the binary point, it is not a proper position. After that we have 0 on this side. So to normalize it, we'll have to shift the decimal point. So we have to shift the decimal point. So this decimal point 1, 2, 3 position we are shifting. So we'll take it as 1.0110, and this exponent we are reducing by t. So will be represented by t. So when we are putting it here, it will also be represented in that way. So this one we did not represent. So it will be 0.0110 and other bits. So this will be the 23-bit say Mantissa part, and the exponent will be same. Now here the exponent has changed. So 128 plus 5, 133. So that is nothing but 6. We have 6 plus 127 is 133. So in that way we have to write it here. So that is the normalized version. Then let us see some examples so that you understand the procedure for conversion. To represent 122.625 in a single precision format. So first we have to convert this 122.625 into binary. So we use the division by 2 method. So 122 divided by 2, we get 61 with remainder 0. Then 61 divided by 2, 30, remainder 1. Then 30 divided by 2, 15, remainder 0. Then 15 divided by 2, 7 with remainder 1. 7 divided by 2, 3, remainder 1. 3 by 2, we get quotient 1, remainder again 1. 1 by 2, quotient is 0, remainder is 1. So 1, 1, 1, 1, 0, 1, 0 in this direction if you go. So 122 will be 1, 1, 1, 1, 0, 1, 0. So that is the binary. Then for the fractional part, you have to multiply by 2. Multiplication by 2. That method we are using. So 0.625 multiplied by 2, it is 1.250 with carry 1. Then 0.250 multiplied by 2, 0.500 with carry 0. Then 0.5 multiplied by 2 will be 1 with carry 1. So 0.625 will be 0.101. So 122.625 will be 1111010.101. Now once this is known to you, then you can follow these steps for the representation. Now here this is a positive number, so the sign bit will be 0. Then the number is 111010.101. So this is the number. Now we have to change the normalize the number by changing the uh, radix point. So now we'll be changing the radix point. So we'll have to shift the radix point. Now this radix point 1, 2, 3, 4, 5, 6 position. So when we change it to this position, we'll get 1.111, then 0, 1, 0, 1, 0, 1. So multiplied by 2 raised to 6. So this is the normalized floating point number. So mantissa part at the right of the radix, that is 23 bits. So we'll have this part 1110100101 and then add all zeros, so that this is 23 bit. Then the exponent part is 6, so we have to add this 127 bias. So exponent will be 6 plus 127, that is 133. So 133 in binary is 1000101, and it is very easy. You know, this is 128 plus 101 is 5, so that is 133. So once you have done all these things, then you can represent it. So this is the sign bit, it is 0 because it is a positive number. Then exponent is this 133, so that is represented with 8 bits. And the mantissa is this part. We have to put this mantissa here. So this will represent 122.625. In this way, we can represent any decimal number in the single precision format. Then let us take one more example, that is the negative number minus 118.625. Now the conversion to binary will not do here, will directly take the number. So the bit here is, since it is negative number, this sign bit will be 1, and the number we are taking in binary, it will be 11101110, that will be 118, and 0.625 is 0.101. So again we are shifting it by position. So here when we shift 1, 2, 3, 4, 5, 6 position we are shifting. So it will be 1.11 and 0.110.101 into 2 raised to 6. So this is the normalized floating point number, and the mantissa part will be to the right of this dot or the point, binary point. So we have to fill it with the zeros. So, and the exponent is 6, we have to add 127 to that. So 6 plus 127, 133. So the equivalent is 1000101. So then we can represent it here. The sign bit will be 1, then 1000101. That is the 8 bits that represents the exponent, and this will be the mantissa, which is here. So this will represent minus 118.625. So I hope you have understood this. You can practice yourself some of the examples so that this is clear to you. And with this we come to the end of this video. If you have any queries, you can contact me on Facebook, Twitter, Gmail or Instagram. Then if you like the video, press the like button, share with your friends. There is a direct option to share in the YouTube. You can directly use this type of button and share with your friends. Then subscribe to our channel Engineering and Technology for You, and don't forget to press the bell icon so that you get notifications for future videos. Then thanks for watching. Have a nice day.